In this video, we are going to talk about single value decomposition. In order to understand single value decomposition, we will first learn about linear transformation. Linear transformation can be performed using three types of matrix: diagonal matrix, symmetrical matrix, and non-symmetrical matrix. So let's start with diagonal matrix. Here we take a diagonal matrix M to perform the transformation on vector X. So here the left hand graph is the original graph, whereas the right hand graph is the transformed graph. And so x in the original graph will convert to 3x and y will remain same. This change is seen due to the transformation of vector x comma y. And so in diagonal, the transform graph was in the same axis as the original one. But we can see uh, when we use a symmetric matrix, then x is converted to 2x times y and y is converted to x plus 2y. As it is seen, as it is a linear transformation, the stretching will be same in will be in same direction, which can be clearly seen when we rotate the original graph by 45 degree. So here we can say that the M matrix is multiplied with a vector I to get a constant time vector I. So here the vector I is known as eigenvectors, lambda I is known as eigenvalue, and the whole equation is known as eigenequation. So this, in case of non-symmetric matrix, x will change to x plus y and y will remain same. So similarly, after few rotations, we will get a orthogonal set of vectors as we got in all the three matrices. So we are going to use this set of orthogonal vectors in the single value decomposition. So here in the original graph, v1 and v2 are two vectors, whereas in the transform graph, m times v1 and m times v2 is the uh, orthogonal set obtained by rotation. So u1 and u2 are two unit vectors in the in the direction of transform vector, whereas sigma 1 and sigma 2 are the length of transform vectors. So transform vector mv1 is equal to the length, that is sigma 1, times unit vector, that is u1. Similarly, we can get the second equation. And now if there exists an vector x in original graph, then we can take components of x along v1 and v2 using the equation x is equal to v1 dot x v1 plus v2 dot x v2, and by multiplying m on both the side we get the next equation. And so now we are replacing mv1 and mv2 using equation 1 and equation 2, and v dot x with is replaced by v transpose x, which leads to the equation mx is equal to u1 times sigma 1 times v1 transpose of x plus u2 times sigma 2 times v2 times transpose of x, and the x is cancelled out on both the on both the side. So we get the final equation, and which can be also written as m is equal to u summation of v times t, where u is the matrix whose columns are u1 and u2, and sigma is the diagonal matrix whose entry are sigma 1 and sigma 2, and v is the matrix whose columns are v1 and v2. The superscript t on the matrix v denotes the transpose of the matrix v.
Now we will see how SVD is utilized to implement dimensionality reduction in Python. Here K represents the number of singular values we have used to reconstruct the original image. As the value of k increases, so does the quality of the output image, as seen on the left. Right now, we are working on making this more user friendly. Thank you.